Good day, all. Today we are looking into Gram-Schmidt orthogonalization process for digital communication. Before jumping into Gram-Schmidt orthogonalization, we shall have a look on how and what is a digital communication system in general looks like. So, we all know in nature we have a continuous sine waves which are distributed along the time axis and an amplitude axis. So to convert them into digital form, we use analog to digital converters, and then we receive the ranges of bits, that is a train of bits, zeros, ones, and so on. And hence these things again to be transmitted on an RF platform, that is again into an analog domain. To convert that we use digital modulation techniques. So such modulation techniques are the what we are going to look into today's video. So hence after this we again combine these continuous waves which are there in the form of sine or cosine combinations. We multiply them again with a carrier signal and then send it out for the transmission. And the same thing passes through the channel and we receive it back, and again we bring it down to the normal frequency using a demod or a demixer, and then again distal demodulation, and which give rise to again train of bits which is b dash. If my input was b, here b and b dash are the bits, and but they can be different. Why they can be different? That is because of the noise that is present in the channel or in the system or in the mistakes when we are decoding them. So those all contribute to the change in the number of bits, but at last we get some train of bits. Okay, so again we use digital to analog converter and we receive back our natural responses with again with an amplitude, time, and hence they have their characteristic of amplitude, frequency, and the phases. Okay, so now our concentration shall go on what is this digital modulation scheme, how is it being used, or what is it different from. We all know in an analog communication that whenever I have my message signal m of t, it is directly with some operation mixed with c of t to produce my transmittable signal, that is s of t. So this operation, whatever that is happening here, is directly done on an analog input message signal, which was similar to this. But in a digital modulation scheme, we have already converted this analog into a digital bits, and these bits have something like this, that is, it has a high and a low and a high and a low later. So they have a bit period and they have amplitudes, but these are no good to send on a carrier signal. If we send, we will be sending only something like on and off of a kind of a carrier signal, but it is no good a modulation signal or a modulating signal. So hence, to convert these signals into a simple sine wave again with a very small band of a frequency, we use something called um, a digital modulation technique, where these B of t is converted using m of t, a simple sine wave or a cos wave or a combination of those waves. We can take that as something like a of t. When a of t and b of t are both combined, we get something called m of t. Here, this is a message signal which is going to ride on the carrier signal to travel through the channel over the receiver. Okay, so today we will look into digital modulation techniques. Now, so already we know our message signal that it is highs and lows within a time period, correct? Consider this is one period and this is made up of two periods. So this is 1, this is 0, this is 1, 1. Okay, so we know that if I group these values in of 1 each, then I have uh, T1, T2, T3 and T4 are the four sections of the time that I need to convert a signal into. So the easiest and the first most modulation technique that one can look into is amplitude shift keying. And in that the simplest most is on off keying or shift keying. So as the word says, on and off, it is something like switching. So these words keying comes from the method of connecting one connector to the other connector. In olden days for the telecommunication switching, we used to use something word like switch and keying. So those words have been incorporated with these modulation techniques. So here on off keying, how does it really look? So this is my message signal with four periods on off keying. Let me represent on with bit with value 1 and off with bit value 0. Here consider it is me who is considering it so. If anybody wants, he can represent on with a 0 bit, off with a 1 bit. That is also true, that is also possible. But it is my presumption to go with on as 1 and off as 0. Okay, so when I represent that in my sine wave, sorry for that. So over the period of on, let me take my A of t, whatever the modulation signal that I'm considering, as something like with an amplitude A sine of omega t. It has a certain frequency, but right now let it be some f. Okay, so how do I represent that? So for the period of t1, that is high, and for period of t2 there is nothing, and between for period t3 and t4 we have our sine wave. Okay, so this is on off shift keying. The same way, the this ASK can be represented with M array ASK. What does M represents? M is equal to 2 raised to n, where n is number of bits that you have grouped. Now we will go here. So for on-off shift keying, that is a simple ASK, you have grouped one bit as one symbol. Okay, what if now I go ahead and group two bits together as one symbol? Then my n is equal to 2. That results my m is equal to 4. What does that m says? That I have four symbols. What are those four symbols? 0 0, 0 1, 1 0, and 1 1. So with this understanding, if I group this in uh, n is equal to 2, how does my signal looks? Here the time period changes. This is T1, this is T2. And remember, for each symbol, I should have different amplitudes. Let me represent the amplitudes as A1, A2, A3, and A4. For simplicity, let us take the amplitudes to be 0, 1 volt, 2 volt, 3 volt, or 1 unit, 2 unit, 3 units of the amplitude. So for 0, 1 or 1, 0, the amplitude should be 2, and for 1, 1, the amplitude should be 3. So let's just mark it. So consider here it is 1, here it is 2, here it is 3. Correct? Here we complete the period of uh, T1, that is what the T1 period it is, and T2 period it is. And then I have amplitude of 3. T2, sorry, T2. So this gives us an ability to represent in a different amplitudes. Now, a first thought process, I just give a thought to this. Now I have something called amplitude shift keying. Can it be something different also? Because each given signal is represented by three fundamental characters, that is amplitude, frequency, and phases. So I can have amplitude shift keying, I can have frequency shift keying, I can have a phase shift keying. So now we will look into phase shift keying. Before that, we will try to look what is a phasor plot or a phasor diagram of a given signal. Okay. We all know the polar plots. What are they represented with in 2D? They are represented with r and theta. What is r? R is the length of the vector, and theta is that angle that it makes with the positive direction of the x-axis. Okay. So for an instant, let us draw it. And now, whatever signal that I take, consider signal A1, that is equal to A sine of omega t. So what is the phase that is there with this sine theta? Phase is 0. And what is the amplitude of this? So the r is equal to A. So hence I can represent this signal along my x-axis with amplitude A and angle 0 representation. In a similar case, what if my A2 was represented with the same amplitude A with a sine omega t plus of phi? And remember, this axis is sine omega t with phi. Phi is equal to some 10 degrees, consider. So then my phi is equal to 10 degrees and still my r is equal to a. So how do I represent that? Somewhere here. This is angle 10 degrees and this is my a2, this is a1 with the same amplitude a and angle is 10 degrees. So in this case, if I represent my ASK, consider the 4 ASK what we saw just a second before. What were our amplitudes? Our amplitudes were A1, A2, A3 and A4, and represented with unit 0, unit 1, unit 2, unit 3. And now we shall represent these arrow marks instead of a complete vector with only one dot. A dot which is there at an distance a from the origin, that is O over here, and at an angle phi from the positive direction of x-axis. So how do I represent these things? They are all made up of a simple sine wave. So that can be represented as a1, a2, a3, and a4. So that is at origin 0, it is at 1, it is at 2, it is at 3. I hope you would consider this to be a proper representation and easy to say many features about the given signal. So this phasor plot gives a better detail about phase and amplitude of the signal. In a similar case, now if I have to change the phase as I have done over here for this phi 1 and phi 2, let us try to represent a PSK. A PSK is phase shift keying. So how is this represented? Let us take the same example of two symbols. A symbol 0 is represented with a phase 0 and a symbol 1 is represented with a phase 10. Consider here again, it's me who is giving a chance or an approach to represent symbol 0 with phase 0 and symbol 1 with phase 10. You can choose any angle you wish. So, as shown in the same phasor plot, let's redraw that. So, this is my symbol 0 and at a 10 degrees, this is my symbol 1. So this can be represented in a similar way. If this is for the 0 symbol, this is for the 1 symbol, and time period difference here. Have a look. It started with a 0 phase, but here when it is starting with a 1, look carefully, it starts at an offset angle and stops at an offset angle. This is that offset of 10 degrees. So what if I increase this between 2 in this way, like at a 0 degrees and at a 90 degrees? What happens? At a first plot, it will be same thing. But at the second plot, it starts at a 90 degrees. Correct? And in the same way, if I happen to represent at 180 degrees for symbol 1 and 0 degrees here, or I can make something like this change for 0 degrees at some 45 degrees, then for a symbol 0 at 45 degrees and for symbol 1 at 180 degrees, then I can have my symbol representations for 0 and for 1 in this way. So it is at 45 degrees, it starts here, and it is 180 degrees, it starts here. Got it? So that is how the entire PSK is represented. The same thing goes again. M array PSK can be represented with multiple symbols at the same time. Again here M is equal to 2 raised to n, and n is number of bits grouping, bits per symbol. Okay, let's have a look for an example, a 4 PSK. 4 PSK. Traditionally, a 4 PSK is represented with a constellation plot or a phasor plot of this kind, where I have symbols 0, 0, 0, 1, 1, 0, and 1, 1 at 90 degrees apart, that is at 0 degrees, at 90 degrees, at 180 degrees, and at 270 degrees. But remember, this is not the only option that one has to represent a PSK. He can represent as his will goes. That is, maybe within a 0 here, 1, like let's take another color. Symbol 0, 0 here, 0, 1 here, 0, 1 0 here, and 1 1 here. But only problem or the difference that would come into picture is one who is trying to decode these symbols back to the bits, he will have a difficulty to identify what is the real difference between 0 0 and 1 0. So the distance what is there between these symbols is very small. So one can mistake 1 0 for 0 1. But when I come back to the traditional representation, we can observe the distance between them is almost of 90 degrees, where one has a larger margin for identifying the difference between each symbols. The same thing goes with higher yum PSKs. So whatever the yum I have, it is 360 degrees divided by yum. So whatever the angle I receive, so that is what is spatial difference between the PSK symbols for achieving best modulation, that is to reduce the least or to get the least amount of error for that given modulation scheme. But remember, this is not the only way. You can do it with any ways. And with understanding of this phasor plot, now we will come back to our Gram-Schmidt orthogonalization. Gram-Schmidt orthogonalization. We have already understood as the space between two symbols increases, it gives us a better margin of error. So, for just a small comparison, if I was going ahead with 8 PSK, I would have had traditionally also only 45-degree differences, which would have made me at a greater difficult task to decode the symbols in comparison to 4PSK. So to solve such a hideous problem or such a problematic way of identifying the phase, we go with Gram-Schmidt orthogonalization, uh, where we will use two reference phases or two or more reference phases which are orthogonal to each other. A small traditional example which I can go with is cos theta and sin theta. And traditionally they are called in phase and quadrature phase. Okay, we all know sin theta and cos theta are 90 degrees apart from each other, and in the contrary to the same thing in PSK we have always used only one phase, that is either sin theta or cos theta. So it can be represented with only one phi, but here we have phi 1 and a phi 2. Okay, but remember, for orthogonalization we can use any n number of orthogonal pairs. That is, I can make a third axis with another orthogonal thing and then use it for another representation. But let us see how does it really happen. So we already know e raised to I theta. What is e raised to I theta? It is a complex representation, or it is a polar representation of a complex number, which can be represented as cos theta plus I sin theta. Traditionally, it represents a circle because theta is not specified as theta goes from 0 to 2 pi. What if I write e raised to I 30 degrees? So that is equal to cos 30 plus I sine 30. So here I can represent that at an angle 30 degrees. Correct? Yes. So, this gives us a proper understanding that any given sine wave or a combination of sinusoidal signals can also be represented on a polar plot with orthogonality. So, here these two are the orthogonal pairs, and this is the thing. First and foremost way of representing the PSK that comes into the picture is QPSK, that is quadrature, phase shift keying. So as the name says, all symbols are 90 degrees apart from each other. So let's draw it. A traditional diagram of a PSK looks as I've just drawn a circle only to represent that it falls on a proper circles. No doubt that all PSK also falls on a proper circle. It was just an attempt to give a better understanding of QPSK. So a QPSK is at 45-degree offset from the x-axis, that is my real axis represented with cos theta, that is phi 1, and a sine theta as phi 2. So when we observe this, we find that it is at an equal distance apart from both the in phase and the quadrature phase axis. So I can write this if I represent a symbol 1, symbol 2, symbol 3, symbol 4. So symbol 1 is equal to cos theta plus sine theta. Symbol 2, cos theta minus minus of plus sine theta. Symbol 3, we have minus cos theta minus sine theta, and symbol 4 is minus plus cos theta minus sine theta. And these symbols can be represented with our combination of two bits, that is 0 0, 0 1, 1 0, 1 1. Fair enough. So this is the representation of quadrature phase shift keying. Once when we observed both ASK and PSK, we know that we can play with two variables here, that is the phase and the amplitude. Then why can't we encash both the properties in a phasor plot to represent our symbols and achieve a better separation between each symbol and have a higher degree of detectability in a reduced way of error? So there where we come with another modulation scheme called QAM, quadrature, amplitude, shift keying. So, what is quadrature, amplitude, shift keying? The word quadrature comes from our QPSK. So that is a 90-degree phase shift between two basic phases and two or more basic phases, and amplitude is the change in the amplitudes of the representation of the signal or the summing of the signals, and shift keying is achieving for different combinations of bits different symbols. So the traditional QAM starts with 4 QAM. and we have simple in phase, that is phi 1, and quadrature phase, that is phi 2, and I have my phasor plot ready, or my constellation plot diagram is ready. So I can have something of this kind, where you can observe it is at a length higher than my y-axis. My x is greater than my y. So hence there's a difference in combination of phi 1 and phi 2's contents into this symbol S1. So S1 is equal to x of phi 1 plus y of phi 2. Fair enough? And the same combination goes with other four. But for my curiosity, I want to test or experiment with something of a symbols represented in this way. Is it not also a combination of four quam? Consider to examine it. So let us take S1, S2, S3 and S4 because it is our representations. We can take however we want. So first line and the second line we should make with a green color, and again back to the blue one. So as we observe, the length of this green and the blue lines are different. So this is at a D1 and this is at a D2 distance. And also they are making different angles with the x-axis. This is phi 1, this is phi 2. We can take theta 1, theta 2, okay? Theta 1, theta 2. Okay, so hence this is also a quadrature amplitude shift gain, but this is in a derived way. This is a more traditional way of representation. We shall see how traditionally different quams are represented. Starts with 4. So phi 1 and phi 2 are in phase and quadrature phase, which will be always there with all the things. I have now 8 quam, 16 quam, remember, what all I'm drawing right now are all traditional way of representation, not really needed to be so. But only thing is, we need 16 symbols which has different amplitudes and phases. And for today's example, the last one which I would like to draw is 32 quam. That is 2 raised to 5, I suppose. Yeah, it is 2 raised to 5. This is 2 raised to 2, 2 raised to 4, 2 raised to 3, 2 raised to 4, and 2 raised to 5. So how does this can be represented? So totally 32 symbols. So and so on, so on, we all go on using for other quams. As per the knowledge, we have 128 or 256 quam being used in our 4G and 5G mobile technology. So these are the algorithms which go into our modulation schemes for mobile communication. And coming to the end of the session, I just want to encash another one concept over there. As we spoke, Gram-Schmidt orthogonalization, mathematically into an orthogonalization theory, we understand that we can have n number of orthogonal pairs. So that is, there can be a orthogonal vector to a given vector, that too they are there in n different forms. That means I can have more than one perpendicular vectors to a given vector. So now phi1 and phi2 are two perpendicular vectors. I can have another vector phi3 which is perpendicular to both phi1 and phi2. So in this condition I can represent my same quam, consider my 8 quam, which I was trying to represent there with four symbols in one quadrant, or in yeah, two symbols in one quadrant, and achieving 8 totally in all four quadrants. Now I can represent it with 4 points in one side of the phi1 and phi2, or the positive side of the phi3, and the negative side of the phi3 I can represent another 4. So how do they look? So consider here a plane there. So this is my symbol 1, similarly my symbol 2, symbol 3, symbol 4. These all are there with the negative z, and I take another term that is at a positive. So this is my symbol 1, symbol 2, symbol 3, symbol 4, symbol 5, symbol 6, symbol 7, and symbol 8. So using three different quadrature phases, I can achieve a better spacing in a three-dimensional way for a symbol for detection. So hence, this concludes our modulation techniques for digital communication using Gram-Schmidt orthogonalization. So what all did we look into? We happen to look into ASK, or prior to that we happen to look into digital communication system in general. Then we looked into ASK, M-array ASK, and we looked into PSK, that is phase shift keying, along with M-array PSK. Then we looked into QPSK, quadrature phase shift keying, then QAM, quadrature amplitude modulation, and M-array QAMs. Remember, for M-array QAM, M starts from 4 to any multiple of 2 raised to n's, but whereas in M-ASK and M-PSK, M starts from 2 to whatever 2 raised to n that one can want, and always the n is equal to bits per symbol. And later we saw, what if I have multiple quadrature phases, and how can I represent my symbols as well? So one who want to do a better research in creating a modulation scheme which can work at a very least amount of power, or at a very long distance, which can withstand the errors that are there in the channel, the fadings of the channel. This is one field of research which is starts from very basic but goes to the topmost requirement of today's communication systems. With this, I thank all